Welcome. So the purpose of this tutorial, we are going to go over the program UCSF Chimera X in molecular modeling, and I'm going to show you how to download a 3D structure of a protein from the protein data bank, and we're going to illustrate how to kind of get something out of it and how to basically visualize the protein so that we can minimize all the extra stuff and get what we want. So the first thing we have the RCSB protein data bank, which is this website right here, and this is available at rcsb.org. So this is the PDB, and there's 215,946 structures available in the protein data bank. And these are X-ray crystal or NMR structures that have been experimentally verified. And so you can download these structures with a 4-digit code and then visualize them and obtain what research you want. The protein I have selected to study here, that's for demonstration purposes, we're going to look at human Cytochrome C. And so we see that we have several human Cytochrome C structures available. I'm going to bring this up, and we have several structures in here. You'll see the 4-digit code right here. So this first one is 6DUJ. This one is 1J3S, etc. Right? So every protein has a 4-digit code, and this is useful for databases because then we can easily access them with this, what we call it, the PDB accession coordinates. Right? I'm going to scroll down, and the model that I'm interested in is 3ZOO. That's the one we're going to use here. This was deposited. Well, let's click on this. And so this is the structure of human Cytochrome C. It is actually a mutant protein. There's just one mutant, which is a tyrosine to phenylalanine mutation. This is from humans, Homo sapiens. And it was expressed in E. coli, so we can see that information there. We also see that it was deposited in 2013 by these authors, Rajagopal, Oral, and Ho. So the method, of course, is X-ray diffraction, which is kind of the gold standard of protein structure determination. And so we take X-rays and zap it at a crystal of the protein that has diffractable crystals, and through that we can obtain the electron density and hence the structure of the protein. Now we don't get hydrogens because hydrogens don't really have many electrons, so we're not seeing hydrogens in this structure. The resolution is very important, so 1.35 angstroms. The lower this number, generally the better. Anything typically less than about 3.5 is typically a very good structure. The higher the number, you're going to have more variability, and you're not going to be able to get as good of a structure from it. You can kind of see what this looks like. Here's the structure itself. There's a paper where we can link to PubMed right here, and we can obtain all the information that they have on this protein that they used to crystallize this paper. And so they've actually analyzed this in detail, so you can explore that paper and download that from the Biochem journal. If we look at under macromolecules, we see Cytochrome C, we see the total number of chains. Now there are 4 chains, which is interesting because Cytochrome C is an electron transport protein, and it shuttles electrons between complex 3 and complex 4 in the electron transport chain. and it's also hydrophilic because it's on the intermembrane space side. There's only one chain in cytochrome C, so there's 4 chains. Well, when this was crystallized, they actually crystallized a tetramer together, which is what was in the space groups of the crystal, and so that's why there's 4. We only need 1 chain. They're kind of identical anyway, so that's not big of a deal there. We see some other interesting information, and we can also have a link to the UniProt database here. And this is, we can kind of see other proteins in UniProt. Now, interestingly enough, if we go to the UniProt database, this is the main structural database of all proteins, but it's a sequence database. It only has primary structure present in it, right? So, but it links to the protein database as well. So we can look up 3ZOO, and we can get right to the entry for human cytochrome C right here. If I just click on this, this tells me exactly everything that human cytochrome C that I want. Electron carrier protein, it's the oxidized form of the cytochrome C heme group, and it accepts an electron from the heme group of cytochrome C1 subunit of cytochrome reductase. Cytochrome C transfers this electron to the cytochrome oxidase complex, complex 4, the final protein carrier of the mitochondrial electron transport protein chain. And so then you can kind of scroll down, you can see binding sites, so you see where the heme group is bound. You can also see where it is bound. You can see more binding sites. This is the iron. There's also another iron here. So the iron interacts with histidine 19 and methionine 81. And then there's cysteines that are in the binding site with the heme group as well. So we're going to actually, you'll be able to visualize these proteins in the binding site, right? You can scroll down, you can get more information, biological information, keywords, different names in taxonomy, accessions, proteomes. There's some diseases information, features. We'll just kind of scroll down here. You can also jump to very specific things. So for example, over here in the left-hand menu, if I wanted to go straight to the structure, I'd just click on structure, right? And then this tells me, now this actually also links, this is another way of accessing the protein data bank with the 3D structure. And so this lists all the various 3D structures in the protein data bank, and it even has for many of them resolution. Now these first 4, it doesn't have resolution because these are NMR structures, so that's a different method. Still perfectly valid, but it's not an X-ray structure, so resolution does not apply, right? And then you see different chains in here and so forth. Then we can skip down to the sequence, and here's the sequence right here. This is the, and it's listed with the single letter amino acid code, all 105 residues. So M is methionine, G is glycine, D is aspartate, etc. And so you can download this as a FASTA file, right? If you click download, here's the FASTA sequence. And this is really just text information, so we can just copy this text, or in your browser you can right click and go save as, and we can just save it. It will by default save it with its UniProt ID with the suffix FASTSA, right? And it just saves it in text format, right? So we can easily save that text file, right? So that's the UniProt database. Back to the protein databank, there's a lot of interesting information about this protein. There's hydropathy information with, disorder, different binding information, etc. And then there's information on all the small molecules that are also bound to this. So in this structure, we have a heme group and we have a phosphate ion that are also bound in there as well. And they have a brief overview of the structure, right? And so that's basically the protein data bank. Now we could either download the file right here in PDB format. That's a standardized text format that we can download. And that just downloads the PDB file. Or what I could do is go into Chimera X, and I'm going to just type Chimera X. Click on that, and then Chimera X will load. And here's my structure. You can see I've actually already accessed the 3ZOO Cytochrome C file. But here what I can do is just simply at the bottom under Command in the lower corner, the lower left-hand corner, just type open 3ZOO. And you'll see the structure appears. So this command, this will instantly access the protein data bank and allow you to download the file. Now there are a couple things to point out about this. First of all, you want to familiarize yourself with using the mouse, right? And so if we kind of use the mouse on here, I'm going to take my camera and maybe aim it down so you can see my mouse, right? And so there's 3 buttons on the mouse. There's the left button, right? There's a right button. I should put it this way. So left, right, and then the middle mouse button is that's the mouse wheel, right? And so you can zoom in and out with the middle mouse button like that. The middle mouse button also serves as a button as well. So you can also have additional functionality there. Now, if you use the left mouse button here, right, this will rotate the molecule about the XYZ axis, and it'll rotate it about a central point, right? Now, the other button, the right mouse button over here, this will move it and translate it in the same plane within the screen, right? So just play around. If you move something too far out, and you can kind of move it back by translating, and then you can kind of rotate it again as well too, right? So that's essentially how the mouse functionality works, right? Okay. So back to our model, if we kind of look at what we've downloaded, we have 4 protein chains, right? And they're chain A, B, C, and D. And if you look in the right window, you see chain A, B, C, and D. If you click on, well, we only really are concerned with chain A because all of these are identical chains, right? This is from, one crystal space group, and so we only need one of these. So click on D and you'll notice that one of these just highlighted in green, outline, and then up here under hide, well, we can hide the atoms and we can hide the cartoons. So if we hide both of these, now D is mostly gone. It's not completely gone because we also have that heme group. Now if I click the HEC, that's going to highlight all 4 heme groups on here. I don't really want to do that, right? I just want to get rid of one of these. And the way to select that, first of all, if you press and hold the control key, and while you're holding that, just press on the background, and that will deselect. You should also be able to deselect by pressing clear right here, but there's a keyboard shortcut with the control key. Then holding control down, use your left mouse button, and I'm just going to kind of capture that heme group, and then we're going to hide that, right? Then I'm going to go over here to C, and I don't need C. So I'm going to hide the cartoons and the atoms. And then I'm going to hold down control, and I'm going to hide the atoms of that heme group. Now then you can scroll through here because you notice the chains disappeared up there. So now press B. We're going to hide that. And then hold down control. And let's select those atoms and hide those atoms as well. Now I can translate. I can press the right mouse button and move in the middle. Enlarge this a little bit. And here is my chain A. And that's my model of chain A, right? Now, one other thing you'll notice, we have these phosphates over here, and so I can get rid of those. So let's go ahead and go to Select, Residues, and these are all the residues here. So these are all the amino acids. But then we have all these up here, so HEC, HOH, and PO4. Well, this is the heme group. This is water, and this is phosphate, right? So if I select phosphate, both of those phosphates are selected. We can hide those atoms, get them out of the way. Then we're going to go to select again now. And remember, we had water in there. So now I have H2O. And now the H2O, interestingly enough, this is only the oxygen atom of the H2O. And with only the oxygen atom present, that means, well, where are the hydrogens? Well, one thing, if you remember, this is an X-ray crystal structure of the protein. And X-rays are so small, and the hydrogens only have one protein. So that amplitude of the X-ray is bigger than the hydrogen atom. So it just goes right through the hydrogen. It doesn't see all of the electrons surrounding the hydrogen, which there's only one. Now for carbon, nitrogen, oxygen, it will actually see all those electrons, so that's how it can get the structure. So we don't have any hydrogens. We could add the hydrogens if we go to Tools, Structure Editing, and add hydrogens. Then we can go ahead and add our hydrogens, right? I just added hydrogens to the entire model, and now we can see those look like definite water molecules, right? But I don't need those, so what I'm going to do now, I've kind of selected just the oxygen. Well, I don't want these waters. I don't need them, so I'm just going to hide them away. They're not really relevant to our model. But the hydrogens are kind of important because that kind of shows the complete model. I kind of like to show that, right? We did see a couple other waters I did not remove, and these are a little bit closer to the active site, right? So if I go ahead and select residues and HOH again, you'll see this water over here and this one, as well as there's one right in front, are a little bit closer to the active site. Now those waters could actually be important, especially if they're in the active site, because they could be bridging interactions within a protein. I think right here I see a hydrogen bond between this OH and the water, for example. So that's also important, right? So that shows us our heme group. That also has kind of gotten a lot of other stuff out of the way, right? So that's also important. Now I'm only showing the heme group in here, and I'm only showing a couple of other residues, right? And so it's not showing the whole thing. If I select control and I highlight everything in here, then I select show atoms. These are all of the amino acid residues in the protein. So that shows all the atoms of chain A and the whole heme group all together, right? So you can see various amino acids, you see some lysines, you see some, there's a serine, I believe, and then we see a glutamate down here. We see a lot of different amino acid residues, right? I'm going to go ahead and just hide all those atoms for now, except I think I want to bring back the heme group in the middle. And whoops, I showed all the heme groups. I didn't want to show them all. So now let's just get rid of that and hide you guys. See, the key with visualizing in Chimera X is to show just what you're interested in, and kind of minimize other aspects of the protein. So, and that keeps things as simple. You know, you want to keep it simple, right? So that's important. Now, this ribbon, what does the ribbon mean? This tan ribbon around here? Well, that is representing the secondary structure elements. So we've got several alpha helices in here. And there's a couple of unordered loop regions, which are really ordered, but we really call those random coils. They're actually pretty ordered. I shouldn't call them unordered loops. But this ribbon, if you notice, there's a beginning and there's an end, right? So it starts at one place, and then it goes all the way through like a spaghetti noodle, and it ends at the other end. And actually it starts over here, because if you hover over part of the ribbon, you'll see that that's where glycine 1 is, right? And if you continue down the ribbon, then this is aspartate 2, and it ends, if you hover over the end, that's glutamate 104, right? And so that basically is the linear sequence of all the amino acids in the protein. That's how the protein has folded, right? If we want to see the sequence, I can go to Tools and Sequence and Show Sequence Viewer. And if I show the sequence, I can show the sequence for all 4 chains, but let's just show the sequence for chain A, and the sequence appears down here, right? And then I can also select individual amino acid residues, like I can select the glycine, and then that glycine has been highlighted in green over here. I can also hold down Control and select the glutamate at the very end. And actually, now the glutamate is selected, but the glycine is not selected. Now, if I press Control and Shift at the same time, I can select both of those. I actually selected the aspartate as well. So again, hold Control and Shift at the same time, and then I did it again. I keep selecting I'm just going to go with it, right? And so then select, G, D, and E. Now, if those are selected, I can come up here to Show Atoms, and I can show all the atoms of those individual residues, right? So now I'm showing the N and the C terminus, and those are the 2 N and C termini, right? So the other thing to look at, now if you remember from the protein data bank, I think if we kind of look at our 3ZOO, actually that's over here. It showed us some info. It's actually up here. So under features, we have cysteine 15 and cysteine 18, and histidine 19 and methionine 81, right? And so if I go back to Chimera X, I can look for cysteine 18. Now if I hover over the sequence, that looks like it's cysteine 14. Let's select these two cysteines and let's see where they are in the protein. So I've got one of them right down here. So I've got two cysteines right here. Now if I've got both of those selected, let's go ahead and show these. There's one of them. And did I select the other cysteine? There's the other cysteine over there. You'll also notice that both of these are actually attached to the protein, right? So we can kind of see how they're attached. And then now, where's our methionine and our histidine, right? So there we go. So histidine, it looks like 19 and 81. I bet this is it, even though it's not showing. I think the numbering is a little bit different here. Well, that's 18, so that's pretty close. And let's see here. Well, what I could do is just, here's another thing. If the numbering doesn't match up, well, just select all the histidines, right? And then I'll select them all, and then we're going to find it. So, oh, there was a methionine, right? It was a histidine and a methionine. Now, if I want to select, I've just selected all the methionines, so there's M, M, and M. There's 3 of them. Now, hold down Control and Shift and go Select. Now select histidine, right? There's histidine, right? I just deselected the methionines now. Okay, so it's not allowing me to do that. Well, let's show, there's the methionines. Now it did select several other methionines outside, so these are in some of the other protein chains, right? But what I can do now, if you kind of rotate this, and I want to get rid of all these, just kind of move it out here. What you don't want to do is select all this and get part of your protein, because then that's going to disappear. So you don't want to do that. What you do want to do is select just these guys. And let's go ahead and hide all those, right? And then so I think this is, there's methionine, and then let's go, there's our well, we've already got the cysteines. Where's our histidine? Histidine over here, right? There's our other histidine. There we go. There it is. Again, it kind of selected all these guys. So let's just kind of select these and hide them and select these. So you do a lot of zooming in and out with the protein to get what you want, right? Whoops, I just selected. I want to do that and zoom in, right? And so now we see a couple metal complex bonds between the cysteine and the methionine right there, right? So you can kind of see that those are definitely in contact with each other. Now this atom in the middle, if I kind of hover over that, that'll tell me kind of what it is. HEC 105. Well, the protein goes from 1 to 104. 105 is just in the protein. It's not part of the protein, but 105 is just the next residue number in the PDB. So when in the PDB file it lists all the atoms, this just is listed after the protein. And it's really part of the protein because this is a prosthetic group, right? And so HEC is the code for the heme group of cytochrome C. So HE, heme, C, cytochrome C. And so that's put in there. And then you'll see the atom type is Fe. Well, we know what Fe is from the periodic table. That is iron, right? So that's our iron atom. We can also hold on Control and select this atom, and we can go to Actions, Label, and we need to label the atoms. I can label the atom by name, and then that iron is actually labeled, right? I can also select this atom as well. That's histidine 18Ne2. So that's specifically the atom of the histidine. And I can even, if I just select that, well, I can label the residue name and number, and that's histidine 18. And I can select an atom up here and label the residue name and number as well. So that way I have those labeled, right? So that's how to label those. Now if I want to get a distance, like if I want to know the distance between, select the iron atom, and if I wanted the distance to this histidine, I need to press Control and Shift at the same time to get both of these selected. And then I can use the distance tool to, let's see, structure analysis, distance, and then with both of those selected, I just press create, right? And then the distance highlighted to 4 significant digits, 2.004 angstroms, right? So we typically use angstroms in molecular modeling because 1 angstrom corresponds to the length of a carbon bond. So it makes it fairly convenient. A lot of our distances come in kind of these, 1 to 10 type distances, as opposed to using the metric system with, if you use this in nanometers, well, this would be 0.2 nanometers, because an angstrom is 1 times 10 to the 10th of a meter, and so 1 times 10 to the minus 10th, I should say, and a nanometer is 1 times 10 to the minus 9th of a meter, right? So the angstrom unit puts everything in kind of a 1, 2, or 3, whereas a nanometer would be a decimal place. So that's kind of the way they do that. And so that's basically how to visualize things, and that's how to kind of clean things up so that you can only visualize just what you're interested in. Now, if you want to look at other contexts in the protein, you could certainly select chain A and everything, and you could, show all those atoms again. which, you know, there's a lot of atoms. That also selects all the waters of chain A, right? And so then, you know, obviously can go to highlight the waters and make those disappear again, and then go ahead and highlight the phosphate and make that disappear again. Again, you still have a lot of atoms in here as well, right? So that's certainly a lot. You can certainly look inside. You can also go to the heme group, HEC, and then if you change, let's see, the atom style, you can make that a sphere, so you can make that space filling, right? And so now the heme group shows up a little bit better, so you can get a better idea of the van der Waals surface of that contact. And you can even look at specific contacts over here. You see this oxygen atom on this carboxylate. There's a hydrogen bond right between those two, right? And so you could, you know, you could highlight this atom and highlight this. I need to select Shift and Control, and then highlight, and then go here to Tools, Structure Analysis, Distance, and I can label another distance, and that tells me that this hydrogen bond is about 2.9 angstroms right there. Now, one thing you'll notice when I measured that hydrogen bond, I selected both oxygen atoms. I did not select the hydrogen. There's a reason I did not select the hydrogen, and that's because to a crystallographer, the hydrogen's not really there. That's not experimental data. And so whenever we measure a hydrogen bond distance, we always measure the heavy atom to the heavy atom. When I say heavy atom, I'm talking about an oxygen, a nitrogen, or a carbon, right? So the hydrogens are not heavy atoms. The hydrogens only have an atomic mass of 1, and so they're considered not heavy, if you will, right? So that's kind of where we always measure a hydrogen bond distance with by measuring the heavy atom to heavy atom, right? So that's kind of how that works. And so I can hide all these atoms again. Then I'm going to go to Residues, HEC, and visualize that again, except remember when I do that, it basically shows all these guys again. So I'm going to select all these, hide that. There's a little bit, you know, we use Mo as well, and Mo's probably a little bit easier. It's a little bit more elegant and less time consuming. That's more of an editor, so we can actually delete atoms. I'm only hiding them. I'm not deleting anything, right? So, and then if I want to select the histidines, select those guys. And then if I want to select the methionines, I'll select them again. And then I've got a whole bunch of others out here. And so then we'll just kind of make these guys go away. And we'll make these guys go away. And now I'm back to my standard model, right? And so then I can kind of look at that, right? And then if I want to, let's say I want to take a screen capture of this, well, I can make a snapshot right here, right? And I just click snapshot. This stored it in C:, it stored it in my username right on my desktop, actually. And it named it image3.png. So now I can go to my desktop, and image 3 is right here, right? and there's my screen capture, right? So that way you can make a screen capture of whatever you want. And that's actually a good way, because you'll notice when it captured that, you could certainly use the snipping tool to also do that, although you're going to get a higher resolution if you use the software, because the snipping tool will capture its screen resolution. The software will actually capture the actual information, right? So that's also important. So basically that is Chimera X, and that is how Chimera X works. I hope you enjoyed this brief tutorial, and if you have any questions, my email is dcashman@tntech.edu. Let me know, and thank you for watching.